Okay, hello everybody. I think it's time to start. Welcome to the 13th BRG webinar. And my name is Bart de Haan. I'm working from the UMCG in the Netherlands. I will support you for this meeting. And I work for 30 years already on encapsulation. But the man next to this picture of mine is Denis Poncelet, and he has far more experience on the encapsulation field than I have. And we have the honor now today that he will present some of the we'll work with. Let's see, how is this going? Next slide, okay. Some rules during this webinar. I will ask you only ask questions by the Q&A, and we do this only at the end of the session, so we will not interrupt the session of Denis. And furthermore, if you have technical problems, you can do that by the chat box. All problems will be solved by Brigitte, Denis' lovely wife, and she's sitting there to help you with all kinds of problems. And as you can see here, it will be recorded, and you can play the podcast later on and see again what has been told. So this webinar is organized with two parties: ENCAPS for Health, the right one, and it's a joint venture for a European Union grant, and it's improving for health benefits and well-being. If you want more information, you can see it on the website as mentioned to the right bottom. And the left part, second party, is the bioencapsulation research group for a huge amount. It has been funded and raised by Denis. And you can see that a lot of effort has been done already. We have more than 80 conferences, training schools, and also the industrial conventions. So it's not only research, but also bringing parties together and trying to help industry. There's 7,000 contacts all over 80 countries, and I think it's a nice group to join. So if you have, you think this is a beneficial webinar, you can also ask to join this group. And there are already 2,200 members. You can see it on LinkedIn. And furthermore, if you need more information, it's on the website as mentioned below. Again, now we're coming to the speaker. The speaker, Denis Poncelet. He was born in Belgium and did his master in Leek, and also his PhD was. I had the pleasure to work with him a couple of weeks here in Groningen, and I can tell you, normally all professors are far away from the working field, but he is still in detailed form able to do nice encapsulation work. And from Belgium, he moved to Canada, where he did a lot of work on university also. From Canada, he went back to now France, where he became a professor, and now is rather retired, but still doing a lot of work for the bioencapsulation group and also working for solving problems for other people. So he's still very tough in the working field. As I already mentioned, he is involved with microencapsulation since 1996, and he is the president of the bioencapsulation group since 1991. And we have organized a lot of events already, and a lot of people are very helpful and also grateful that, for instance, what kind of working groups are performed, and you can teach and be the teacher yourself later on. So I think it's time now for Denis to start the presentation, and I hope you will all enjoy. At the end of the presentation, we are able to ask questions. So enjoy. Denis, the floor is yours.
Okay, good. Welcome to everybody. Then I will make a presentation on the dripping technology, which is, I think, evaluated by industrial, especially. I will try, in fact, just to explain you a little bit. The principle of the dripping technology is that if you have a nozzle, a needle, and you extrude a liquid, for low flow, you will get, in fact, a drop per drop formation. But if you increase the liquid flow, you will have, in fact, formation of a jet, and we will see, in fact, that this jet could be broken in droplet. If you go too far in the flow rate, in fact, you will form a spray. These two regions, the jet and the drop per drop, is, in fact, the dripping. And in fact, what you will do is that you will drop the droplet in most probably a jellyfish bath, which will form, in fact, the capsule. You have some equation that describe when you switch from drop to the jet regime is a little bit not as clear when you switch from the jet regime to the spray, but this is probably not so much important. I want to make my presentation not only science, but also talk a little bit about the technical aspect. And the first thing is that you need some equipment. And then you can make some homemade system, and you see some of the equipment we have built in our lab. They are not as nice, obviously, than the commercial equipment. And if you want to use it, it means that you have to be a little bit innovative and have probably a good workshop. And probably most of you will go for the commercial equipment, and I place here mainly the three most important provider of equipment for encapsulation by dripping. If you know all the group, I will be happy to know it. I especially, in this presentation, use some information coming from NISCO, because he have different kind of equipment, and all of them have their own specificity and their strength, and then probably if you want to have an equipment, you have to think about it. One big question when you make dripping is that you have to have a constant flow. If you work with a low flow, probably the searing pump is the best solution. If you want to increase the flow, especially to get the jet, you may need to work with a pressurized vessel, which is a little bit difficult to control, because if the viscosity of your solution changes from the same pressure, you will have different flow. But now it exists some system which is measuring the flow and compensate in this. Another option is to use some pump. The peristaltic pump is giving pulse, but by using two heads, you may try to damp, in fact, the pulse. And probably the pump which is the most used, especially in the commercial equipment, is the gear pump. You will need also some injector. You know, the most simple one is just to use a needle, which is quite interesting if you make a small volume. But if you start to want to have a high flow, it's probably better to have some injector, which will be, in fact, not a long tube like in the needle, but an empty tube with a small hole at the end. And then I give you here one system, which is the cone, which is compatible with the needle, but you can have also some stainless steel. Obviously, if you buy a commercial equipment, they have their own nozzle, which is well designed for the type of application we have here. And generally, the whole is done with the laser system. Now, let's start with the drop per drop. The flow you can get from it is from mainly 1 milliliter to 200 milliliter. You know, you may say 1 milliliter per hour is probably quite low. As Bart already told you, I was working with him last month, and he's working mainly on encapsulation of pancreatic islets. Then he have only a few hundred islets. then it's no question to have a billion of capsules, and already 1 milliliter per hour, allowed to have 250 capsules per minute. Then in a few minutes, he will already have used, in fact, whole of his pancreatic islet. Then in function of the size, the type of application, you may need very low flow and you may need high flow, and we haven't go to jet regime to get very high flow. Now, the system is that you have just a needle and you extrude with the needle. And I will show you a first movie which is based on the multi-needle built by NISCO, and you observe that you can have quite easily a high flow if you multiply the number of needles. But look carefully, you see that in fact the droplet is detached from the external size of the needle. And this is quite important, because when you would like to define what is the size of the droplet, in fact, the droplet detached when the gravity force, which is mg, is equal to the surface tension. And as you have the mass of the droplet, you can deduce, in fact, the diameter. If you try to take this equation and in function of the external diameter, you observe that, in fact, mainly you will have droplet, which is between 2 millimeter and 3 millimeter. It's no interest to have such big capsule, especially if you want, for example, to make an injection. I mean, one big question is that how to reduce the size of the droplet. And you have different techniques. I will, in fact, show you mainly two. The first one is to place around the needle some air jet, and the air jet will, in fact, push the droplet and be added to the gravity. I show you here again one movie coming from NISCO, and you see, in fact, the droplet is around 1 millimeter in place to be, in fact, 2 or 3 millimeter. This system is developed by BART, and especially have set up some system in the way that it can, in fact, really center the needle in the middle of the system, which is quite important, in fact, to get some very nice entrainment of the droplet. What happened is that you have the equation I showed you before. You had the mass of the particle, the droplet, and then you have, in fact, the surface tension. And you will add two additional forces, one which is the laminar flow entraining the droplet, and one which is the turbulent flow, which is also making a drag force on the needle. I make this graph long time, more than 30 years ago, when I was still working with Professor Neufeld in Canada. And you see that between the model and the data, you have a difference. And the reason is that in this equation, we don't take in consideration something important, is that turbulence means vibrating the droplet. And then this provokes the detachment of the droplet faster than we expect from this equation. But it means that this phenomena is a little bit random. And then if you have this too much vibration, you will not get, in fact, a monodispersion. This is why probably you can go to lower the size to 500 micron, but not, for example, to a few micron. Another option, and this is something we have worked together with BART last month, is to use the electrodripping. Again, I take this equation, and in this equation, you have the surface tension. The surface tension is the tendency of the droplet to attract themselves on the surface of the droplet. But if you apply an electric potential on the droplet, you have charge on the surface, which will, in fact, create some repulsion and reduce the surface tension. As you remove the surface tension, you see automatically that the mass of the droplet will be lower. Again, I show you one equipment which is developed by NISCO, and Francisco Acevedo from University of Frontera in Chile is working with me this month, and I asked her to make a movie to show you, in fact, how it's working. She didn't change the flow rate, but she increased, in fact, the electric potential. And you'll see at some stage that the number of droplets increase. And they become smaller because as the flow is the same and you have more droplet, obviously the size of the droplet is smaller. This is a little bit more mathematical description. You see that for when you don't apply, in fact, the electric potential, you have the size that we was expecting from one of the previous slides. As soon as you introduce an electric potential, this surface tension will be corrected by a function of the electric potential. But you observe that if the potential is equal to some critical value, this term becomes zero. And in this case, in place to form droplet, you will form a jet. And we will see, in fact, a little bit later why, but then the diameter of the droplet will be mainly 2 times the internal diameter of the needle. Okay, now we have described a little bit how to make drop per drop, but especially if you are industrial, you are not looking like Bart to make 1 milliliter per hour. You would like to make a lot larger quantity. And by increasing the flow, you can go from liter per hour to even a quite large quantity per hour. And we even make one system in our lab. When we had work with a few nozzles, we expect working with 8 hours per day and 160 days per year. And with such system, we was able to define a system which was able to produce 500 tons per year. Then we are really on a different level of work than the drop per drop. The first system to break the jet in droplet is to apply a small intensity vibration. The idea is not to shake the nozzle, but to introduce a small vibration. And you see this small vibration will create a contraction of the jet until the contraction becomes so big, then in fact you have a detachment of the droplet, you know. I show you again a little bit one equipment, which is based like this. You will especially look at the fact that you have some line here and you have some light, and I will explain you why we have such equipment on it. It's to have a narrow side distribution with the resonance technology is that you have to avoid all vibration. Even a magnetic stir on the table may bring some trouble. And you have to apply what most people call the optimum frequency. And I prefer more and more to call it the natural frequency. Because if you don't apply something, if you avoid all the vibration, this is the frequency that the jet will break. If you apply yourself the natural frequency, you will have a nice size distribution, you know. But if you apply a frequency which is not the natural one, your system will be the combination of a natural frequency breakage and the impulse vibration. And then in this case, you will get sometimes large size distribution, but you can even get 2 peaks. And even you apply vibration, so more often, the natural frequency will be more important and will have a bigger peak than the vibration you have done. Now, how to define this natural frequency? And I give you some equation. I will not go through the detail, but let's go to the conclusion. Mainly, the diameter of the droplet you form is near to 2 times the diameter of the jet itself. And I give you here, for example, the type of flow you can expect in function of the nozzle based on the Buchy description of their own system. Now, obviously, when you have equation, they work very well until you make experiment. And especially in this equation, probably they didn't care so much about the viscosity of the solution, especially the elastic velocity, viscosity. Then probably this, working with this frequency will not be exactly the natural vibration. And this is where you have tricks. I will start by showing you how we have observed the formation of the jet using a fast camera. And you observe that when you observe with a too low frequency, you have the impression that the droplet going up. When you observe with the right frequency, you observe that in fact the droplets seem to be fixed on the in front of the camera. If you have a too high frequency, you observe that you have the impression that the droplet go down, and even if you have really far from the good condition, you can have a coalescence of droplet or even breakage satellite and so on. You may understand it. Let's assume that I will take my hand and I will open my hand every second. And you take a picture every second. If you take a picture every second, you will have the impression that my hand don't move. But if the frequency of your picture is different than 1 second, you will see probably a movement of my hand in one way or another way. And this is what happened here. Now, this is with a very fast camera. This costs a lot. And commercial equipment don't have a fast camera, but they have some LEDs. And this is the light you saw on the NISCO equipment. And the LEDs is flashing at the same frequency that the vibration you apply. And in this case, you can, in fact, observe you can observe it's not as clear that with the fast camera, but you can observe if you have the impression that the jet is moving or not in front of the LEDs. And when you find this condition, you know you find the natural frequency. Now, it's one constraint with this system is that the viscosity is a constraint to liquid to move. Then if you have a high viscosity, you will have a damping effect. In place to have the vibration which will contract more and more the jet, you will have a damping effect and then you will not have a good breakage, you know. And the general rule is to say that the viscosity must be lower than 200 millipascal seconds in the way that the system works well. Another thing is that, as we saw, the flow will be function of the nozzle size. And if you take a too small nozzle, most of the time you will block it, you know. We generally observed that under 200 micron, it was quite difficult, in fact, to have a constant flow. It was often blocking at some stage. Then probably the droplet will not be lower than 400 micron. I say, just one remark, I say the droplet, but if you make capsules, often you have a contraction when, in fact, you will have the jellification. Okay. Another option to break the jet is, in fact, to take a wheel with some wire, and then you, in fact, pass the jet and turn the wheel at high speed. It was developed by Professor Vorlop, but it's now, in fact, mainly work and developed by Genialab. Unfortunately, I'm thinking that they don't sell so much. Again, NISCOF make one equipment, and I will show you the movie. You see here you have the whale, you know. We will see it sooner. Then the whale is turning at glass speed. You have the jet passing through and cut in droplet, you know. To define the size of the droplet is relatively simple in theory, is that the volume is equal to the flow divided by the rotation speed times the number of wires. And then you see that in function of the rotation, the number of wire, and the size you want to get, you can have flow which is quite high. One remark is that when the wire cuts the jet, some part of the energy is used to cut the jet, but some part is giving some kinetics effect on the jet, and then the jet is deviated. And this deviation is more important if you have a low viscosity. You have to make a high flow to have a jet which is relatively strong and use, in fact, relatively high viscosity in the way. Then you see in some way is that the resonance technology and the jet breakage, you know, it's two techniques that can not so much concurrent, but are probably proposing two options in function of the properties of your liquid. If you really want to go even to higher flow, one option is probably to go to replace the gravity by a rotating centrifuge force. Then in most of the equation I showed you before, you can replace, in fact, the G by the centrifuge force, and then you can get quite high flow. The problem in this case is that first, probably you don't get a so nice size distribution, but also you need a room which is quite big. Then it's a question I always ask myself, is that, is it better to have more nozzle or to have a rotating system? Probably one system which is quite amazing to see is developed by a French company. They make a disk and they flow, in fact, the liquid on the disk. Then you form some jet which break in droplet. They manage to avoid all the vibration, which is really difficult when you have a rotating system. And they apply the optimum frequency. And you see that you have a very nice size distribution using this system. Then if you look in summary, if you want to make big droplets and low flow, you can work just by gravity. If you want to make a small quantity but small capsule, you can use either the air-driven system or the electro-dripping. If you use the jets, you can use either the resonance technology or the jet breakage, and then you get, in fact, a flow which is higher. But for me, theory is a few hundred micron the limits. You know, you can multiply the performance by making multi-nozzle, and as I told you, you can probably work with a centrifuge system, but then probably you need a large room. To give you an idea, one of my friend in USA is a room which is 100 square meters to work this system. That, for example, if you want to sterilize, it's not so easy to sterilize a room of 100 square meters. Okay, we have until now mainly made droplets, and you didn't come to my presentation to listen how to make droplet, but how to make capsule. And we will go through different technologies. Some technology make some beads, and some make what people will call really microcapsule. But as the active ingredient will be dispersed in the beads, is still part of the microencapsulation. Probably the best well-known system is the alginate, which is dropped in a calcium bath. And in fact, the calcium will in fact make a link between the alginate chain, and in fact, it will form a jet. The project NCAP for Health, as you learned at the beginning of this presentation, is devoted to use pectin in place of alginate. And this is why I was with Bart Laartmans to, in fact, try to develop this technology. But you have many other kind of material. And for example, I give you the chitosan, which is a positive polymer, could be, in fact, jellified in presence of phosphate. An important remark about it is that you make hydrogel beads, which means you will have 2 to 5% of polymer, and the bead you got is porous beads. Some people pretend that they will be able to encapsulate drugs and something like this. Maybe if you dry them, but most of the time, the molecular cutoff of such kind of bead could be a few 100,000 Dalton. An alternative to the ionic gelation is the thermal gelation, and you can use, for example, the carrageenan, agar, or agarose, and by dropping a warm solution to a cold KCl solution, you may have the jellification. But you can also inject this carrageenan in a cold air, and this has different advantage because you will avoid, in fact, the bath. You don't need then to make a filtration. You don't need to make a washing. And you can even, if you have interest to make a dry capsule, you can go directly to a dry process. I show you here one system we have developed in our lab. You have, in fact, the MEL solution, and then you have, for example, the cell suspension. You will mix them. It's interesting to mix them just before the extrusion in a way that the cells will stay at high temperature for a very short time. Then you drop them through a cooling column, and you collect them at the bottom. And I will show you a small movie. Then you see, in fact, the jet passed through the column, and we collect it at the bottom, and you can directly use them like this, or you can, in fact, dry them if you want. I will not go through the detail of the equation, but this is just to say we have did a little bit of modeling of this process. And the size of the column you need is probably maximum 2 meters, which is something you can even probably build in your lab. Another alternative to the thermal gelation is, in fact, to use a melt material, for example, a fatty acid or a paraffin or something like this. This, in place to make gel, you will get, in fact, directly solid beads. And the solid beads will be hydrophobic when most of the hydrogel will be, in fact, hydrophilic. It's a big difference between the two systems is that the jellification enthalpy is really low. Then you don't need so much energy to cool down the carrageenan droplet. When you use, for example, the stearic acid, you need a lot of energy to cool down, in fact. And in this case, you will have not a column of 2 meters, as I described for the thermogel, but you will have probably need to have a high tower if you use big beads. And I show you, for example, one system which is developed by Airbus Spraytech in Switzerland, and the column could be up to 20 or 30 meters high, probably something a little bit difficult to install in a laboratory. You have now, I will go a little bit quickly through the different technology to show you the diversity, because it's plenty of different technology to transform the droplet in a capsule. For example, we have work, we inverse the system, we take calcium suspension and we drop in alginate. And then in place to have alginate bead, we get a core with a membrane of alginate. You can do something similar by dropping glutaraldehyde in the chitosan solution. And you see here, for example, some capsule we have done, which a layer of alginate surrounding, in fact, a whole face, And even more than this, you can drop the alginate in a chitosan solution. Alginate is negative and chitosan is positive, and they will interact at the interface. And this make, again, some real capsule membrane with a liquid core, you know. And if you have really, especially the system cellulose, sulfate, and this special quaternary amine, they haven't succeeded to go to a molecular cutoff which is 3000 Dalton, a lot lower than what you expect for such kind of system. And the last system I would like to show you is that you can complexify your equipment. And I think most of the suppliers propose some equipment like this. In place to extrude one liquid, you can extrude two liquids. And in this case, you can form a core shell capsule. And here, for example, you have capsule we have prepared with a whole face in the middle and, in fact, an alginate layer. But we have also developed some capsule when you have a hydrophobic layer outside and aqueous solution inside. And then you have a high versatility with such a system. It's a little bit more complex than making a single extrusion because you have two phases, you have to care about the position of the nozzle, the dimension of the nozzle, the flow of each one, and so on. But you could succeed to do it, and then this is a really nice system. Before to conclude, I would like to give you a few advice to succeed to make a good dripping. First, you need a fast gelation system. If the gelification is not fast enough, what happens is that your droplet will probably deform before to be gelified. You need a solution, the dripping solution, which is a higher viscosity than the bath viscosity. This is generally the case, except, for example, in the interfacial conservation, because in this case, you have a polymer in the bath itself, then you have to work. But for example, Francisca is working now in my lab, and she's producing pectin chitosan capsule, and she succeeds quite well to make the capsule. The surface tension of the bath must be low, and probably it's important to introduce a little bit of surfactant if you have too much problem. You can play on the height of the nozzle, especially, for example, for the jet cutter, the linear velocity of the jet is quite high. And then if you don't want the droplet to explode on the surface, it's probably better to have a certain distance in the way that you allow a gentle entrance. Make a small vortex, at least at lab scale, make a small vortex and collect, in fact, the droplets at a half distance from the center. And then the movement of the liquid will entrain the droplet inside the liquid quite fast. And then you will have a nice gelification, if I can say, on all sides of the droplet. Then you will get, in fact, spherical capsule. I gave you some idea about the rule to make the dripping. Respect this rule, and you will get a low side dispersion. Then in conclusion, I will say that the dripping technology have a large selection of dripping methods, allow you that going from milliliter per hour to probably tons per hour with a low size dispersion, which is not the case, for example, for the spray technology. The spray technology could even go to higher production. They make even smaller capsule, but you have a large size dispersion. You have a large selection of capsule formation, which allow to form different structure, bead, capsule, and so on. You have different material, which could be hydrophilic or hydrophobic. In general, the material is cheap, but be careful. For example, the alginate, the normal alginate is a few euros per kilo. But if you purify it for a biomedical application, it can go up 3,000 or 4,000 euros per kilo. It can be applied to many domains, food, fish, cosmetic, biomedical. This is the most important one. They are biodegradable. Yeah, often use natural polymer. You can even think about make capsule which will be vegan. Then at least it's an alternative to consider when you are working on encapsulation. But I don't know why it's not so much industry working on the dripping technology. And I plan to organize some webinar on industrial microencapsulation, probably in September, October. And I will ask, in fact, to Thorsten Brando from Brace to talk about the large-scale production that he has developed, which is probably very interesting. I thank you for listening my presentation. You have my email, you have my website. Most of my publication is on it if you are looking for some. And I will be really happy to answer now to your question, but also if you have question later, don't hesitate to contact me. It will be a pleasure to answer. Bart, I'll let you start again.
Applause for you, Denis. Thank you for your very nice, clear presentation, and give people insights and information on how to start and how to proceed the encapsulation procedure. It was well documented. I have a question, and it is from Florian Pias, and he's asking, how do you rate microfluidic flow focusing, so using fluids as a continuous phase to dripping, to force dripping, in comparison to the dripping technology presented? And he says, obviously, it's predestinated for smaller droplets, but besides that, what are the main advantages and disadvantages of both approaches in your eyes?
Okay, I will say that first the microfluidics and millifluidics, which is are evolving a lot in the last few years, and things are changing. A few years sooner, I was not expecting that you can develop a real process. Now, the fact that you can make very small droplet of controlled size have by itself some application. And I work on one project that a long time ago, when the microfluidic was not developed, it was the idea is to have 1 cells per capsule. And for doing it, you need very small one. This is the kind of application when obviously the microfluidics will be helpful. Some companies more and more say that they are able to produce larger scale with the microfluidics. And even we had one webinar when we had the presentation of 2 technology, which was, if I can say, derived from the microfluidics and allowing to produce larger scale. Probably the bigger difference is that to make a microfluidics, you need to have 2 phases. One phase is the, let's say, the alginate. And then you need, for example, a oil phase. And then when you arrive at the end, you have to clean the capsule. When in the dripping, you will have alginate falling in the calcium. And then probably you need to filter them and just wash a little bit with water, which is probably a big advantage in regard to the microfluidics. The microfluidics flow probably also to make some kind of special structure. I have a friend that I've developed a technology, I try to remember the name that he put on it, but he managed to have a capsule when half of the capsule is one material and half of the capsule is another material, you know. It's something that probably I expect it will not be so easy to do with the dripping. Even one of the experiments we did last month, we tried to make capsule of pectin alginate, and we observed that we had a structure which was a little bit similar, but not probably as well defined that with the microfluidic. And I think it's different technology. It's not, dripping is not the solution for everything. It's one alternative that the people could consider. Emulsion is another approach, spray is another approach. I don't think they are even concurrent. They are fixed, they are allowing to make different kind of capsule for the thousands of applications that exist in the world.
Okay, thank you for this clear answer. I hope Florian Kias has also enough information for you. If not, Florian, please do not hesitate to send an email to Denis for further explanation. There are no further questions anymore. Shall we proceed with giving them some information of the future events?
It's just one more, which just appeared.
Oh, yes, sorry. Anonymously, Anthony. So he's thanking you for the presentation. It was very interesting. Do you think that encapsulation of hydrophilic solution using drop-and-drop or jet break technologies is possible?
It depends what you are, not so much on the fact that you encapsulate some hydrophilic solution. Alginate is mainly 98% of water, then it could be a hydrophilic solution. Probably the question on the back of it is that you would like to keep them wet. If you keep them in a beaker close or in a bag that will be closed, or if you keep them in water, it's not a big problem. But as soon you put them on, for example, on the table, don't dream. The alginate beads dry as fast as a water droplet. Then it depends a little bit what you are looking for. Is that, for example, I'm working on one project actually with Christophe Lacroix in Switzerland, when you want to make an encapsulation of some probiotic. But the idea is that to keep them wet and then introduce them in the reactor and make a production of the probiotic. Then it's okay. Now, if I will take this capsule and put on the shelf, very quickly they will dry. Then you will lose, in fact, probably the interest. Another point is that even you will put in water, if your hydrophilic material is low molecular weight, it will escape. For example, we have, when we want to see the capsule, we sometimes put a dye inside the capsule. If you observe them quickly, it's okay. But if you wait for, let's say, 20 or 30 minutes, most of the dye will have migrate to the solution. You know, which means it depends a little bit what you are thinking by encapsulation of hydrophilic solution, and especially what you want to do with them after.
Okay, thank you. Is there anybody else who would like to share or ask a question via the Q&A?
Apparently not.
I think this will be the last one. So again, thank you, Denis. Shall we now proceed with the acknowledgement of the future events? Yes.
Yes, you have to probably share your screen.
Yes, I will. Yes. Oh, this is now gone. This is the. Sorry for the mess. So we have some future events, which are, of course, everybody could join and register. We have the 21st Microencapsulation Industrial Convention, and it's in Chicago, USA. It's around spring 2023. And so if you're from industry or you want to join, please register at the Bioencapsulation.net, as mentioned below. And further, we have a next webinar in September, October, and this is about industrial microencapsulation. So for everybody, thanks for joining. I hope it was a nice lecture for you all, and I hope to visit you all next time. Thanks a lot, and thanks, Denis, for giving this nice presentation.